Okay, good afternoon, everyone. People, the service was a little bit delayed. People who went for lunch, still they are feasting their cake. So I will start. Celesta is here. Later she will come because from the matter of time, Mike is saying that we should go ahead because people have flights. So basically, I have to speak here, right? I don't like all these mics and stuff. Okay. I'm going to talk about on fire performance of structural members when you bring in polymer concrete or polymer modified concrete. Okay? This is a project which we are doing with NEX, ACI NEX. And the project, I think our partners are Utah State University, Srishti Banerjee. She's the co-PI. She's here as well. And my student is here. I will talk about it. So first, quickly, I'm going to give you some background information for what are these polymer concretes, which others will talk in more detail. But I will talk a little bit on fire safety, why it's important. Then, what are the performance? Concrete generally is excellent in fire, but when it comes to polymer concrete, what are the performance problems? Some of the recent studies, still it's ongoing, the project. What are some of our results we are going to present? And this is too early, we need a lot more work, but some preliminary ideas we have for making this fire tolerant, little bit at least. So basically, as you all know, to address sustainability, resiliency, you name it, all this durability, a lot of new concretes are emerging in the market. One such is polymer concrete, which is a composite material that uses polymeric compounds as binders. Okay? Either you replace completely with cement or partially with cement. When you replace it completely with cement, it's polymer concrete. When you partially replace, it's polymer modified concrete. We also have polymer impregnated concrete, which has applications in precast concrete. It often is impregnated, but the cost is higher here compared to this. Typically, we replace 15 to 30% or 100% in these two types. When you have this, it's much more sustainable, fast curing, durable, high strength. All this is possible just like new generation of other concretes. Lot of applications in overlays, bridge overlays and stuff, but there are applications in buildings as well. That's important, keep that in mind. What are the typical properties? You can see this is our conventional concretes, not anymore, which used to be we are using in 80s and 90s. We compared most of that with that, right? So if you see here, the compressive strengths, you can get significantly higher strengths, even modulus you can get, high modulus as well. And flexural strength, it all matches very well with those properties. When it comes to thermal properties, which is important from this point of view of this presentation, they are slightly high, but not all that different, but there is very limited data on this kind of stuff. That's unfortunate. So I won't go too much with all this data. We did some of that work, but this is from the literature. Now, what are the performance problems when it comes to polymeric concrete? This is much more at high temperature, but typically, this is a new generation of concrete, any one of this. Okay, the characteristics, what you are dealing with in design is the binders are either epoxy resins, mostly for polymer concrete, or SBR latex for PMC. That's the current way of doing. We have a lot of additives sometimes added, such as basalt fibers, aluminum hydroxide compounds, and dense microstructure, low permeability, brittle. These are some of the issues. Then, when you use in structural members, maybe you might have lower concrete cover because it's highly durable. Why do you want to waste it to get more moment capacity and stuff? Lot of advantages: superior strength, durability, sustainability, economical. There are disadvantages. One of them still we are struggling with, and the industry also is addressing this: mixing placement issues, odor, right? And ready mix plants, they are not ready to, as soon as you say that, they run away. They don't want to do that, at least in smaller towns. And when it comes to fire, there are much bigger problems. Rapid degradation of the resin. Resin degrades basically because the polymer transitions from glassy states to rubbery state and to flowy state. Okay, as you can see that very quickly, once the glass transition temperature is exceeded, you start the problems, and that glass transition temperature is around 80 to 90 degrees centigrade depending on the binder. Rapid reduction in strength and stiffness properties. You see polymer concrete is somewhere here, and conventional concretes are here. Strength versus temperature as a percentage of initial strength. Okay? So then you have significant variations because you are using different types of binders. It's not like Portland cement concrete where consistency, even there you have differences, but here it's much worse. So all this leads to lower fire resistance when you use this, or high temperature tolerance in structural members. So current design provisions, including that in ACI 216.1 is the fire standard or IBC, won't be applicable for this. Now, why fire is important? Fire represents a significant hazard and threat to the built environment. Especially in buildings where life safety plays a major role. This is the statistics for buildings in the United States in 2023. 1.4 million fires, 3,670 fire deaths. So it's a big problem. So if you want to use it in building applications, fire resistance or structural fire safety is very important. Basically, your structural member has to have, we call it, certain ratings. Even in 9/11, as you see, much of the damage around ground zero, when we went there for investigation, much of this was because of the fires. 40 buildings suffered some level of damage or complete collapse. So from that perspective, obtaining good fire resistance is important. Second thing, that's for buildings. Even in bridges, fire is becoming an issue because we are transporting too much of chemicals, petrochemicals, right? And we are using a lot of these new materials. So there has been number of bridge failures, bridge collapses because of fire, including I-10 bridge in the West Coast, second most traveled highway, I-95, East Coast, most traveled highway near Philadelphia. So there is number of bridge fires where polymer concrete as an application, as you know, bridge overlays and stuff, is an issue. Currently, what do? We put in two kinds of systems. If it is in buildings, we put in sprinklers, heat detectors, smoke detectors, etc. These are called active fire protection systems in buildings to kill that fire at an early stage. At a later stage, if you want the building or the bridge to stand up till the firefighters come in, which takes half an hour, 45 minutes, your structure has to stand up. That is the fire resistance rating for a structural member. So your structure has to withstand the effects of fire for that 1 hour, or in buildings even 3 hours if it is an hospital building. So that kind of stuff is hard to get in polymer concretes. Conventional concrete, no issues. You can design that using the current one. UHPC, harder, much harder. This is much, much harder. So that's why this research project is important, to develop strategies. So conventional concrete, how do we get this fire resistance 2 hours, 3 hours? All you need is provide sufficient cover thickness and make sure your member is sufficiently wider and deeper. That's all you need, right? So ACI 216 has it. You can get 1, 2, 3, 4 hours easily in a beam or a column. Now, when it comes to polymer concrete, that cover thickness as well as your size of the member, these ones won't work. Now, so I will skip this. This is for columns, ACI code. This is what says if you need a limestone-based aggregate concrete, 2 hours of fire resistance, you provide 10 inches, the minimum dimension here, and you provide for a column of 2-inch concrete cover. That's the design is done. Now, we are doing a lot of work. Because of lack of time, I will just quickly go through this. You see, first we developed a set of concrete mixes for evaluating under high temperature how they perform. This is for material property test at this stage. Two groups, one is polymer concretes, polymer modified concretes. What's the difference? In polymer concretes, it's epoxy resin which is mainly used. Polymer modified concrete is SBR latex in this one. Then literature talks about little bit, you can improve this with little bit of additives. So we decided to explore this and fully put it to rest. Two kinds of stuff. One is basalt fiber and ATH. We supplemented this in addition to this small quantities. They are good flame retardants, but fire resistance we wanted to see. Developed lot of material properties. This is, look at here, normal strength concrete, the red line. This is how strength drops with temperature. These are all tests done in the lab. Now, if it is polymer concrete, can you see this here at 100 degrees itself? It becomes, okay, yes, I mean, don't go from here to here jump, maybe it is little bit here and then it's jump, but overall, once the TG is crossed, very highly. Literature, nobody has done this kind of test before, they all did the residual strength test, in a residual. This is hot state. That's very important during a structure when fire is burning, whether the structure holds up that load or not. Now, this is polymer modified concrete overall, okay? Similarly, elastic modulus based on time, let's skip that. Thermal properties, which is very important to, that's the one which gives the fire resistance to a structure. This is thermal conductivity. This is conventional concrete, red line, polymer concrete, as well as polymer modified concrete has higher thermal conductivity. That means heat spreads quickly within the member, okay? Similarly, we did specific heat thermal expansion, but notice here, when it comes to polymer concrete, very hard to go beyond 200 or 300, even the material property test. You cannot do this. Lot of smoke. Police were called in our lab when we were doing the test. You know, health and safety issues. Fire department came in, kicked out all the samples through it. Number of problems we faced is very hard at high temperature. It emits the smoke. People get headache. Nobody can be around. Okay. So notice that. But PMC, because it has less resin content, we could go up to 600. We ideally in fire design, you need up to 800 degrees for structural design in buildings. In bridges, you need up to 1000 degrees. So even doing the test is problem. Then, very quickly, I'll show you some of this. We developed a computer model. Everyone knows ANSYS and Abacus. We used, in this case, Abacus, I think. Yeah. So the basic discretization of the structure, and then we developed all this fire data. We evaluated this under ASTM E1195, which is the standard we use in US, what the temperatures are. Once you get it, you get the material properties as an input, get the temperature rise in the structure. Once you get the temperature rise in the structure, you can determine how much load carrying capacity it has at 5 minutes, 10 minutes, 20 minutes, 1 hour, 2 hours. You can keep going, repeating this. It's a time step analysis, right? Till the failure happens, right? Then once you go, we validated it. Not against polymer concrete beams at this stage. We want to do, I was talking to Mike there to fabricate some beams for us or find some sources. At this stage, we couldn't do it, but we did. For example, this is how deflections vary with time in a conventional concrete beam, normal strength concrete beam. Okay, model versus test data. As you can see, test data is solid line, dashed line is this one. Temperatures here itself, what happens at the rebar level, the temperatures here, how they rise with temperatures, okay? So this is normal strength concrete beam, remember. One thing you should notice, failure typically occurs when it's around 600 degrees. Even after 3 hours in a normal strength concrete beam of this size, it doesn't reach failure. I mean, in a simplistic way, okay? And it fails maybe in 3 hours. Same thing we did, same model, except we brought in some of the issues, performance problems with polymer concrete and polymer modified concrete through material models. And then we analyzed very much similar beams. Look at two things. Here, the temperature in the corner beam, in the polymer concrete here. Can you see here? You reach that 600. Remember, it was not, at 3 hours, it was not reaching. At 30 minutes itself, you have about 400. At less than 60 minutes, you will have nearly 600 degrees here in polymer concrete because of the high thermal conductivity of these materials. Polymer modified concrete are better. This is the normal strength concrete beam. Here as well, normal strength. This is the polymer modified concrete beam. Notice here at about close to 2 hours, you will get that 600 or something. So it delays in the case of the polymer modified concrete. So this is the temperatures in the rebar. This is at the mid depth. We will, you can read that in some paper later. Don't worry about it. Now, how about the deflections, how they compare? This is the mid-span deflection in this beam versus time. Look at here, polymer concrete. In fact, this is surprisingly, when we add basalt fibers or basalt fibers to this one, right? Look at here what happens. ATH or basalt fibers didn't too much help, right? On the other hand, this is the normal strength concrete beam, polymer concrete beams, just polymers, 100%. When you have only partial replacement, can you see this here? Normal strength concrete beam, it is getting there 90 minutes, 100 minutes. So, it is possible polymer modified concrete beams with some basalt fibers and this kind of stuff and other strategies to get up to 2 hours somehow or the other, or at least 90 minutes. So, there is a scope for this. Then following this, this is the moment capacity, again very much similar, polymer concrete, normal strength concrete. How the moment capacity drops with time, it starts to drop after TG very quickly, we are nothing up to 400. Polymer modified concrete versus normal strength concrete, these are different additives which are added. Now, very fire resistance, what happens? Normal strength concrete beam, look at this, the same beam only made with conventional concrete up to 3 hours. If you have polymer concrete, 20 to 25 minutes at the most. If you do polymer modified concrete without any additives I talked about, you are right here. But if you add additives, you get little bit more enhancement. Can you see that? Little bit more enhancement. I mean, this has to be still, we are struggling with, all the parameters and stuff, but it's possible. Now, these are preliminary guidelines, I said. I mean, it might change, but currently what we are working on or thinking about is how to make sure these polymer modified concretes can go into the field, if at all, if it is used widely, is in fact going into ACI guidelines and stuff, is polymer concretes are very hard to get reasonable, this thing. It's impossible to move that 20 to, typically in buildings you need 1 or 2 hours, 2 hours mostly, it's very hard. So, what's the approach? Additives won't help too much. It may be flame resistant and stuff, but not from the point of view of fire resistance, structural fire resistance, protective insulation layer. So, if at all if you want to go, put some kind of a good protective insulation layer. So, we are working on that at present by coating. You see here cylinders at the cylinder level because of the complications involved in high temperature testing. If you go to PMC, polymer modified concrete, right, you saw that it's good. So, all you need, we are proposing not insulating. Insulated become expensive, it also adds, if you insulate it, go ahead with that. Otherwise, adjusting the cover thickness, maybe small dimensional changes is possible, that's one possibility. Second possibility, obviously putting the insulation, and even without both these, it may be possible if we play around with this, but still it's preliminary. So, this is what we are looking at it, okay? And for this to do, you need a lot of material properties and advanced analysis. So, what can be done at this stage? We can conclude that polymer concrete is a good construction material, it has its applications, okay? From sustainability, economics, performance point of view. However, there are performance problems, especially under fire. So, they have lower fire resistance compared to conventional concretes. Polymer concrete much lower, polymer modified concrete bit lower. So, we need experiments as well as further research to develop some kind of a design strategy for using this in building applications as well, okay? So, I think basically at this time I want to take this opportunity to thank ACI 548, I'm spelling it out right, Polymer Concrete Committee. We took a lot of guidance as well as Professor Taha and Mike and his team helped us as well in mixing and other things as well. So, and more importantly, I would like to thank NEX for sponsoring this, and Jersey unfortunately is not here. So, but you are here, yes. No problem. And I want to thank my co-authors, Srishti, Ahmad, and as well as Manish. They are from Utah State University, their team and our team. Thank you all. And hopefully in the next session, next ACI, we will present more. Thank you.